In this video, I'm going to discuss three cases that cause a limit not to exist. So typically when you're dealing with a limit, we had something of this nature where we said like, x went to 5 and we had x squared minus 3, and that by direct substitution equal 25 or 22. If your limit equals a number, it exists. So this limit exists and it's 22. Just as to recall, as x gets close to 5, this function gets near 22. So in order for a limit not to exist, one of three conditions have to be in place. I'm going to say limits do not exist if one of these three things happens. Divergence, left and right don't match. In 3, is the rare one, uncontrolled oscillation. So for the first one, divergence, if you have a limit where once you evaluate the limit, it seems to be getting larger and larger forever, that's a case where the limit diverges and it doesn't exist. So let's just look at a really simple case. The limit where x goes to infinity of just x squared. If you were to plug in a number here for x that gets greater and greater and greater as x goes far to the right, basically here, what happens to the y? It does not exist because it diverges. If you think about a graph, this parabola, as x goes right, y is going up. So that's why this limit doesn't exist as x gets really big. Something that's really easy to do is forget that limits are always based on what's right here. So just because the function x squared doesn't have a limit as x goes to infinity, that has nothing to say. Sorry, how about we do x goes to 4. When x goes to 4, just ignore that. We've got a 4 here, a 16 here, and as x gets close to 4, y gets close to 16. So everything in calculus is pointwise defined, which means at every particular x value, what's happening could be different. And so this limit doesn't exist when x goes to infinity. It does exist when x equals 4 or any other number. Let's try another one where we have a diverging situation. Let's try this. So x approaches 4 for the function 1 over x minus 4. As x gets really close to 4, say that's like 4.001 minus 4, the bottom is going to get really small. And as the bottom gets really small, the size of that fraction is going to get really large. So this is going to, the graph, there would be an asymptote at 4. And the graph would look like this. So as we get close to 4, you can see this graph starts going super, super high. 4 minus 4.001 minus 4 is a very small positive, so 1 over a small positive is a big positive. You can see that right here. If we had a number just below 4, maybe 3.999, that minus 4 is a small negative, and that would be 1 over a small negative makes a big negative. That is reflected right here. So this is a case where the limit doesn't exist because of divergence. The second reason a limit doesn't exist is because the left and right don't match. So a piecewise function is probably the most common way to see this. Let's just write an example down. 3 and let's just write this function down. This is a piecewise function. When x is 2, the function changes from one piece to another. So if I just draw this graph real quick, when x is 2, here's 2, 1, 2, 3. We're going to have an open dot and open dot. And that graph looks like that, just a flat line at 3. And then also, if I were to put something close to 2 in, we would have a closed dot at 5, up 2 over 1. You can see this graph would kind of do that. So you can see that as we come close to 2 from the left, the y is remaining at 3. And as I come close to 2 from the right, my function is coming down close to the number 5. And so if I said the limit here is x gets close to 2 from the left for f of x, and then the limit is x gets close to 2 from the right for f of x. From the left side, my limit would be 3, and then coming down from the right side, my limit would be 5. So that causes the two-sided limit not to exist because the left and the right don't match. Now, the one-sided limits do exist. If I said, what's the left-hand limit of 2, that would be 3, and the right-hand limit is 5. So sometimes we can talk about simply a one-sided limit, but the two-sided limit does not exist because the left and the right don't match. Another example of this is with the function absolute value of x over x. Quick graph. At 0, this function is undefined, so nothing at 0. But if you went just say put in positive 1 for x, you would get here's 1, negative 1. You get a dot right there. If you put in positive 2, absolute value of 2 over 2 is 1. Basically, you have an open circle at 1. It goes that direction. At negative 1, the absolute value of negative 1 is 1. Over a negative 1 makes a negative 1. So this side goes like that. So over here, if I did limit as x goes to 0 for g of x, this does not exist because left limit does not equal right limit at x equals 0. Now, there's something kind of perplexing about this problem. I asked you about the limit where x equals 0, or x, goes to 0, and the 0 is actually undefined. And with limits, that does not matter at all. If we're talking about the neighborhood around a point, it really is the neighborhood around that point. It's not the point itself. If the point itself is not defined, you can still discuss limits around an undefined point. In this case, it didn't exist, but it didn't exist because the right and left sides didn't match. It had nothing to do with the point x equals 0 being not a part of the domain in function g. So this is an interesting example to look at because it kind of just illustrates to you that the point itself has nothing to do with the limit at all. So the last reason the limit doesn't exist is called uncontrolled oscillation. Also remember that any other point on this function g has a limit that's defined. Okay, this is okay. Let me just kind of draw a quick little picture here. We'll have, call that 1, -1. So for this graph, for the function sine, if x goes to infinity, the graph is going to begin like this. And then as x continues going to the right, we'll have another period, and another period, and another period of sine. And this keeps going. I'm going to put a little arrow on this to indicate that it keeps going as x goes to infinity that way. So this is kind of a difficult thing to talk about because it's not diverging. It's staying completely kind of contained in this upper +1 and -1. The sine function goes up to 1, down to -1, and periodically bounces back and forth between the two. So this is not diverging. It's also not converging. To converge, you have to have a certain value that you kind of smash down on and don't leave as x approaches whatever is right there. So this limit does not exist because of uncontrolled oscillation. Some people confuse this and they say anytime there's a trig function, oh, it's uncontrolled oscillation. That's not true at all. This is a very kind of unusual case. Let me show you a couple more. If you had the limit as x goes to pi for sine of x, here's you can look at the graph 2 pi, 1 pi. This limit as x goes to pi, you can see as we come to the pi from the left and from the right, that limit equals is 0 because sine of pi is 0. You can just evaluate that with direct substitution. So that's an example of a trig function that actually has a limit. Also, you could say the limit as x approaches pi over 2. This is probably not necessary, but that's a half. So that's simple. You could have something like this where x goes to 0 and you've got sine 1 over x. This one's a little trickier. If x goes to 0 here and you try and make that go to 0, 0 is undefined because it's in the bottom of the fraction, it's in the denominator. But if you have 1 over a super small number, if we're not putting in 0 but instead a really small number that's close to 0, then you end up with a 1 over a super small, which makes this whole thing gets big as x goes to 0. And what's sine of a big? Well, up here you saw the sine of a big did this, up, down, up, down, up, down. The bigger x got, x getting bigger is going that way. The sine just keeps going up and down, so this does not exist, and it's the uncontrolled oscillation. So when you look for this type of reason a limit doesn't exist. Remember, it's very rare. It's the least likely thing you're going to find as far as a reason a limit doesn't exist by far. But for some reason, anytime a trig function comes up, half of the students will just say, "Oh, that doesn't exist." So make sure that that you're right and that you apply this the way you're supposed to. Most trig functions do have limits. You plug them in, and that's that.